Hey, this is lesson 1C, equations with two variables. So far in all the work we've done, you've been solving equations with one variable, like the one we have here, 2x minus 5 equals 11. We have one variable there. And when we solve that, we find that we have one solution. Like, try it. You would add 5 to both sides, and there's only one answer you can get after you add 5 to both sides. So you have 2x equals 16. Then you divide by 2 to cancel out multiplying by 2. There's only one answer you could get when you divide 16 by 2, which is 8. So the one solution is x equals 8. There's only one number that you can put in place of the x to make it come out to be 11 when we do the math, and that would be 8. So when we put 8 in there and we get 16, 16 minus 5 is 11. But there's only one number that we can put in there. So when we have an equation with one variable, then we have one solution. Now, if that variable occurs more than once in the equation, we still call that an equation with one variable. So if we have something like this, 3x minus 2 equals 7x plus, let's say, 19. Well, that's still just one variable. But when we put them all on the same side of the equal sign by subtracting 3x from both sides, see, they are like terms. We can combine them together. So that would be 4x plus 19 equals negative 2. Then it's similar to the problem that we had just moments ago. And we would subtract 19 to get negative 21, and then divide by 4. Let's see, so that would be negative 5 and 1/4. Now we know that sometimes when we have an equation with one variable, then we have two special cases where we have an infinite number of solutions, or we have no solution, but those are special cases. So if we have something like this, 3 times x minus 2, and on the other side we have something like 2x minus 6 plus x. Well, when we use the distributed property here and we have 3x minus 6, and when we combine like terms over here, then we have 3x minus 6. Then we have an infinite number of solutions. Because any number that we put in place of the x will make the left side equal to the right side because they're both 3x minus 6. Or if we subtract 3x from both sides, we'll notice that all the x's cancel out, and we end up with something like negative 6 equals negative 6, which is always going to be true, so any number will work for x. And we have a similar case where we might have no solution. But those are special cases. So generally, for an equation with one variable, generally, we have one solution. Okay, sometimes we'll have an infinite number of solutions. Sometimes there will be no solution. But that happens usually when we have all the x's cancel out, which really gives us an equation with no variables. So in this section, we're dealing with equations with two variables. So let's take a look at one of those. Now we have an equation with two variables. I started with a really simple one, x plus y equals 11. And I have a couple of questions about that. Since we have two variables, like how many solutions are there, and what do those solutions look like, and how would we check it? So think for a second. What two numbers, because we have two numbers here, x and y, what two numbers add together to 11? Now, if we were in a classroom situation, I know that we would probably have 18 people in class, and we'd probably have 18 different answers. Well, maybe not 18, but a lot of different answers. Because some of you would say, oh, yeah, well, 10 plus 1 equals 11, or 9 plus 2 equals 11, or 8 plus 3 equals 11. And somebody who's thinking outside the box would say, well, negative 99 plus 110 equals 11. See, we have positive and negative numbers. They do exist. And somebody would be thinking outside the box, and they would think, well, 6.5 plus 4.5 would equal 11. So we have decimal answers also, which means there are an infinite number of solutions. Infinite number of solutions. Now, this is a little different than the infinite number of solutions that we had when we were talking about the example with one variable, because, see, these don't cancel out. We don't end up with like all the variables canceled out and 11 equals 11. We don't have that. We have an infinite number of solutions because there's an infinite number of pairs of numbers that add up to 11. So all of those have to come, all those solutions have to come as a pair. See, 10 isn't a solution by itself. 10 and 1 would be a solution. 9 is not a solution by itself. 9 and 2 is a solution, and so forth. So those have to come in pairs. When we have two variables, the solutions come in pairs. And if the two variables are x and y, then there's a certain order we like to write those pairs in. And so we call those ordered pairs. And every ordered pair of numbers would be in the form of x and y. So that 10, 1 solution would be 10, 1. Or it could be 1 and 10. And those would be two different solutions. They're not the same. Because when we graph them, which is what we're going to be doing, 10, 1 and 1, 10 are not the same point. 10, 1 would be across 10 up 1. 1, 10 would be across 1 up 10. Two different points. Those are two different solutions. So the order matters because the order changes the actual solution when you change the order. So how would we check it? Well, we still check it by taking the numbers that we have and plugging them back into the equation. So if we thought the answer was 8, 3, and x equals 8 and y equals 3, and we have x plus y equals 11, we still take the 8, put it in place of the x, the 3, put it in place of the y, still do the math to make sure that the left side is equal to the right side. That's still how you check it. Okay, but since there is an infinite number of solutions, we can never list them all. Can never list them all. That's where the graph comes in handy, because we can graph them all. We can't list them all, including all the decimals and all the fractions and all the negative numbers, but we can graph them all. So that's what we're going to be doing. So here are some of the solutions to x plus y equals 11. And let's take a look and see what the graph looks like. So some of these will not fit on my little coordinate plane over here, because my little coordinate plane only goes up to 10 in the x direction and 10 in the y direction. Just for a little review, the origin right here in the middle is 0, 0. And to the right is positive and up is positive in the x and y directions. So to the left is negative, so that's negative 10 over here. And down is negative, so that's negative 10 down here. And every point is an ordered pair. So I'm going to start with 110 because that fits on our graph. 110 is across 1 up 10. That would be right here. Now, the 0, 11, this is a special point, and we do want to include that, even though it doesn't fit on my little coordinate plane here. You have to imagine that the coordinate plane is infinitely large, but we can only draw a small part of it because our paper is not infinitely large. Our mind, what we can imagine, is infinitely large. So sometimes we have to imagine it, and we can try to represent it on the paper. 0, 11 would be across 0, up 11. That would be about right here. That's an important point. 0, 11. That is different from 11, 0. Remember, 11, 0 would be across 11, up 0. So this one is 11, 0. But those other points, let's put them on here. 110, we already have 2, 9 is across 2, up 9. 3, 8 is across 3 up 8. 4, 7 is across 4 up 7. Can you see something happening here? Across 5 and up 6. Across 6 and up 5. And you should notice that if we kept going in our table, which we could do because we could find more x and y values that add up to 11, then they would all end up on the same line. So since these all up in a straight line, when we graph them, I'm going to go ahead and connect these, because when I connect them, what I'm doing now is including all of the fraction and decimal values in between, and I'm going to put arrows on the ends because that includes all of those positive and negative numbers that we could have for x and y. And so that graph represents our infinite number of solutions. Infinite number of solutions. And since it's connected, that's all the fractions and decimals. And since we have arrows on the ends, it goes on forever in both directions, including all positive and negative numbers. Okay, since this one is a straight line, this is a linear equation. That's where we're going to be dealing with mostly, is linear equations. Because in linear equations, we have special things that we want to learn about concerning linear equations and how to graph them. And you'll notice as we go along that there will be patterns that form those straight lines. And the patterns on the x and y side of our little table that we made for our solutions. Okay, so that is an equation with two variables. All right, go on and see how would we find the solutions for this equation. Oh, good question. Well, this equation is set up a little differently. Notice that the x variable is over here on the right side, and there's a whole bunch of stuff that we have to do with the x, but the y is kind of like by itself. So the way this equation is written so that we have to do the math with the x to find the y. So it's like you could choose the x, put that into the equation to get the y. So that is like an input-output table, and the x is the input. Okay, we also say that when y is the isolated variable, we also say that y is a function of x. When the y is the isolated variable. When the y is the isolated variable. Which means we can take some x values, whatever they are, it doesn't matter, because remember, we're probably going to have an infinite number of solutions. So we get to choose like whatever we want to put in there. Now, you probably want to choose nice, easy numbers to put in there for your x values, to put in there, see, because that's our input. So we're going to put those in, and then we're going to figure out what the y is after. So if we choose, let's say 0, then to find the y, we would take 1/2 times 0 minus 3, because we put 0 in place of the x. 1/2 times 0 is 0. 0 minus 3 is negative 3. Okay. Choose the next x value. I don't want to choose 1. I want to choose 2. So if I choose 2, and then I have 1/2 times 2 minus 3. 1/2 times 2 is 1. 1 minus 3 is negative 2. Let's choose 4. Why am I choosing even numbers? Because every time I choose a number, I have to multiply by 1/2. If I choose an odd number and multiply by 1/2, I get a fraction. I don't want to have fractions. Really, fractions are harder to graph. So I'm going to choose 4. 1/2 times 4 is 2. 2 minus 3 is negative 1. Do you see a pattern emerging? Hopefully you see a pattern emerging. If I continue to choose even numbers, 0, 2, 4, 6, 8, 10, then my output values, my y values, should continue the same pattern that I have discovered so far. Negative 3, negative 2, negative 1. It looks like I'm adding 1 every time, so the next one should be 0, and then 1 and 2. And you can test that out. At the end, you can take 1/2 times 10 minus 3 and see if you get 2. 1/2 times 10 is 5. 5 by 3 is 2. Yes, it works out at the end. So those patterns are important because it helps make the math go faster because we don't have to do as much math because we notice the pattern. So nice. So when we plot those points on our graph, remember it's always x first then y. So 0, -3 is across 0, down 3 right there. 2, -2. 4, -1. Okay, see a pattern here? 6, 0. Are they in a straight line? 8, 1, 10, 2. Now, if we're graphing something that we think is a linear equation, and we get a point that's not in a straight line with the other points, then it's possible that we made a mistake on that one. Might want to go back and recheck your math. Okay, so the linear equations, notice that there's no exponents on the x or y. That would be a good indication that it's linear. There's other ways that we can tell it's linear, but if there's no exponents on x or y, after the y is isolated, then it's probably going to be linear. There's other things that we'll talk about later. And then we could draw that line. Now the line goes forever in both directions, so I'm going to follow the pattern all the way to the end of my graph here to make sure my line is good. This program I'm using does not have a straight line tool, so I'm just freehanding this. Put arrows on the end because it goes on forever in both directions. And there we go. So that pattern that we found, keep that in mind. The output pattern, remember, it was going up by 1 every time. The input pattern for the x, remember, we were going by even numbers, so that was adding 2 every time. And whenever we go from one point to the next point on the graph, like from this point to this point, we had to go up 1 and over 2. 1 in the y direction, 2 in the x direction. You might remember something called rise over run, 1 over 2. Maybe you remember that. That would be awesome. Okay, let's see what happens on the next one. So how would we find the solutions to this equation? Well, this equation is not in the same form as the last one. So in the last one was easier because we had input and output, remember? The input was the x, the output was the y, and it was easy to find those because all we had to do was put the x into the equation, do the math, and find the y. But in this one, the y is not the isolated variable. We can fix that. So the first thing we're going to do first is we're going to solve for y, which means we're going to isolate the y variable. To isolate the y variable, we have to solve equations just like we did before, except now we don't have all numbers. All right, so let's take this and move this down a little bit here. So to isolate the y variable, we have to cancel out this plus 2x. To cancel out the plus 2x, we are going to minus 2x. Subtract 2x on both sides. So this positive 2x and this negative 2x will cancel out on the side where the y variable is. And if we write these in the order that is mathematically accepted, is like the variable term first, then the constant term after that, that would be negative 2x, and that's a positive 12, so it becomes a plus 12. See, now y is a function of x. Now it's easier to see that x is the input. You could do the math to find the y, which is the output. So now it's easier to make an xy table. Now there's another reason we want to do this too, and you might already know what it is. But choose some x values and find some y values. It's nice to start at 0, but sometimes you want to throw some negative numbers in there for the x, but choose your x values in a pattern. Now in this one, I'm just going to choose 0, 1, 2, 3, 4 because I'm not multiplying x by a fraction. Okay, 0, 1, 2, 3, 4. And 4 values or 5 values, or that's a nice number to pick for your x values. So the y, all we have to do is negative 2 times 0 plus 12. Negative 2 times 0 plus 12 is 12. So negative 2 times 1 plus 12. Well, that's negative 2 plus 12, which is 10. And negative 2 times 2 plus 12, oops, plus 12. That's negative 4 plus 12, so that's 8. See a pattern emerging? Looks like it's going down by 2. Down by 2. So go down by 2 again. To go down by 2 again. See, now that we have a pattern and we can recognize the pattern and keep the pattern going, it makes the math so much easier. Let's plot those points. Now 0, 12 doesn't fit on our graph, but if it did, it would be up here on the y-axis because it's across 0 up 12. So that one up there, 0, 12. That becomes an important point for us. And so 110... Actually, plotting these points becomes easy if you just count from the previous point to the next point. So I'm not going to go back to the origin and go over 2 and up 8. I'm just going to start with my previous point that I had, like 110. And then I know that every time I go 1 in the x direction, right? So I'm going to go across 1. I have to go down 2 in the y direction. Or I could go down 2 in the y direction and across by 1. So down 2 in the y direction, across by 1. There it is. Down 2 over 1. Down 2 over 1. And that's the same pattern that we had. There's our 4, 4 point right there. So that pattern we're using... the rise over run that I mentioned earlier, rise, in this case it's negative 2, the run was 1. That is right here in our table, right there, negative 2 over 1, and there's the 1. That is the change in y over the change in x, which is also, that's triangle there is the Greek letter delta, which is change in, for math and science people. Change in y over change in x. And that is also known as the slope of the line. Now the slope of this line is negative. Notice when the slope of the line is negative, that when we draw the line from left to right, which we read from left to right, so we're drawing the line from left to right. Keep in mind I'm freehanding this, doing the best I can to stay in that pattern. It goes down. So you're going down this way, down, because the slope is negative, right? Slope equals negative 2 over 1. Or we could just say negative 2. And it's just understood to be over 1. Okay. Now, in our equation, this slope of negative 2 is in there, but only after we have isolated the y. The slope is in the equation only after we isolated the y. See, we isolated the y variable. When we wrote this equation, we were going for something special, and the special thing we were going for is this form of the equation, y equals mx plus b. Okay, the slope is the m. M, well, there is a reason that it's m, and that would be because in Latin, in the language that we write a lot of our math and science terminology, it's modulus, which means change in. In modern times, some people say that m just stands for, that's how you can move from one point to the next point, which would also make sense. because from one point to the next point, you would move by going down 2 and over 1. Rise -2, run 1. That's how you would move from one point to the next. Now that b number that we wrote there, see y equals mx plus b, the b is 12. And in this case, that's where we began to make our points. But that 12 will be always the number that's left if x is equal to 0. And that point is always on the y-axis. That is the y-intercept. Very nice. So we are going to solve for y to isolate the y variable. We're going to write the equation in this form, y equals mx plus b. Then we can use the b, the y-intercept, to begin drawing the line. B for beginning, begin there. And the m for how to move to get to the next point. Now that m, there's a lot of different uses for this m. That's how you move to get from one point to the next point on the graph. But it's also the rate of change when we have a word problem. The slope is the rate of change. Remember, it's the change in y over the change in x. That is the rate of change. Hey, you're taking notes on this? I thought you might want to. Okay, so let's see how we would do that for this one. Okay, so we're going to try to find solutions to this equation. Remember, there's an infinite number of them. We're going to try to write this equation into the form of y equals mx plus b so that we can use this slope and the y-intercept to help us graph the line. Because here's what I would not want to do. I would not want to make a table right now without changing this equation and try to choose some x values and solve for y, because that is a lot of work. Because let's say if I just chose x to be 2. Okay, I'm going to have to put 2 in here, and then I'm going to have to multiply, subtract 6 from both sides, divide by -2. That's a lot of work. So I'm going to solve for y one time, put it in this form, so that I don't have to do so much work every time. Okay? So let's try that. So to isolate y, so in this case, this 3x, we have to cancel that out, and it's positive. That's a positive 3x, so we're going to add negative 3x to both sides. Okay, so we got rid of the 3x over here, so all we have left is that negative 2y. See that minus sign in front of the 2y makes that negative 2y. And then I'm going to write these in the order that I'm going for. Remember, I'm going for this order right here. Now, I won't be finished because y is not going to be isolated yet. But so far, I have negative 3x plus 8. Because to isolate the y, I have to cancel out that negative 2, which is multiplied by the y. To cancel out a multiplied number, you have to divide. So we're going to divide by negative 2. And now on this side, I need to divide that whole side by negative 2. But there's 2 terms. And when there's 2 terms, that means I'm going to divide each one individually by negative 2. So basically, I'm dividing all terms by negative 2 when I get to the dividing part. Now, this multiplying by negative 2 and dividing by negative 2 cancel out on the y. So we have y equals. Now all I have to do is simplify. When we simplify this one, we have negative 3 over negative 2. We're going to write that as 3 over 2. Because a negative over a negative is positive. So that's positive 3 over 2. Then we have our x. Okay, then we have positive 8 divided by negative 2, and positive 8 divided by negative 2 is negative 4, so minus 4. Okay, now this equation is in the form of y equals mx plus b. Okay, remember what the b number stands for? B is the y-intercept. That's where we're going to begin to graph the line. And the y-intercept is -4. If we let x equal 0, then this 3/2 x will become 0. So when x is 0, the 3/2 x cancels out. And then the y value that's left is -4. So 0, -4. See, we could put that on the graph like right now. 0, -4 is across 0, down 4. There it is. There's our y-intercept. Okay, the m number, remember that's how we're going to move to get to the next point. The modulus, the change in y over change in x. So the slope, which is the m number, is 3/2. And you really want it to be a fraction because the top number is the change in y and the bottom number is the change in x. And it's positive. Remember, it was negative over negative, but we reduced that down, simplified that to positive 3/2. So the change in y is +3, the change in x is +2. Now, positive slopes go up, right? +3 would be up 3, 1, 2, 3. +2 in the x direction, over 2. Notice it's 3/2, so we go up 3/2. Interesting. Okay, and we keep doing that. Up 1, 2, 3 over 2. Up 1, 2, 3 over 2. Up 1, 2, 3 over 2. I'm out of room. I could keep going forever, but my graph is not that big. Now, if you want to leave it negative, if it's -3 over -2, then that would be down 3, but then the -2 for the x, that would be to the left 2. So from our y-intercept, if we go down 3, 1, 2, 3, to the left 2, that's -3 over -2. So you remember, -3 over -2 is on that same line. That is a positively sloped line. A positive slope goes up from left to right. Nice. So the characteristics of any linear equation that we are using to help us graph the line would be the slope and the y-intercept. Actually, I should have said them in the reverse order, the y-intercept, because we use that first. We begin with the y-intercept. It's a good beginning point, and that's the B stands for begin here. When x is equal to 0, that point is going to be on the y-axis. All right. So change the equation by isolating the y to put it into the form of y equals mx plus b. Identify the slope, the m number, and the y-intercept, the b number, and that will help you graph the line. Begin by putting a point. See, the b number, the y-intercept, that's a point. The m number is not a point, it is a set of directions on how to move to get to the next point. Okay, so don't put a point at 3, 2. That's not what this slope means. Okay, let's try another one. So here's one. It's already in slope-intercept form. If we use the slope and the y-intercept to graph this line, we should be able to do it without actually writing any work, which I know some of you are going to love that because you don't like to write out your math work, even though I recommend it every time. Here's what I am going to write. I'm going to write the y-intercept. I'm going to abbreviate that. And that's -5. Okay? Now, you could write 0, -5. That would be okay. But the y-intercept tells me that it's on the y-axis, so it is 0, -5. So I have that point here. And the slope on this one is 1 over 3. So that's rise 1, run 3. Rise 1, run 1, 2, 3. Rise 1, 1, 2, 3. 1, 1, 2, 3. And there's where my line's going to go. See, using the slope and the y-intercept makes it so much easier to graph the line. But notice I want to follow the same pattern from the beginning of the line to the end of the line, so I put dots all the way to the end of my coordinate plane that I have. Partly because I'm freehanding this because I don't have a straight line tool. Okay, that's all there is to it. Now, if the equation is not in slope-intercept form, see, then you have to change the equation. You have to solve for y to put it in this form, and then find the slope and the y-intercept. Okay, so I think that maybe you should pause right now. Take this equation right here, 5x minus 3y equals 6. Change it into slope-intercept form. That's called slope-intercept form because we have the slope and the y-intercept, slope-intercept form. And then when you're done, unpause the video to see if you are correct. Okay, did you subtract 5x from both sides? Then did you remember that that was negative 3y? Did you divide by negative 3? So now you have y equals a negative over a negative, which is positive 5/3. Did you leave it 5/3? Yeah, don't make it 1 2/3. Don't do that. 5/3, rise over run. And that's negative 2. 6 divided by negative 3 is negative 2. So the slope is 5/3. That's the change in y over change in x. The y-intercept is negative 2. And hopefully you got that. And when you started graphing the line, you started it on the y-axis at negative 2. So keep in mind the y-intercept we could find without doing all of this. If we went back to the original equation, I know I'm like off topic here. Okay. If we went back to the original equation and I said, okay, find the y-intercept, then what you have to know is at the y-intercept, which is like on the y-axis, it's always across 0, which means this is the y value when x is equal to 0. And we could find that without changing the equation. Just put 0 in for the x. And if you do that, that's going to be 5 times 0, which like cancels itself out, minus 3y equals 6, which is really negative 3y equals 6. And if you divide by negative 3 to isolate the y, you get the y equals negative 2. See, that's what we got. The y-intercept is negative 2. So you don't always have to isolate the y in the equation to find the y-intercept. You just let x equal 0. Keep that in mind because we're going to use that in just a little bit. But anyway, let's finish with this line. Our slope is 5 over 3. That's rise 5. That's in the y direction. Run 3. That's in the x direction. Rise 5. 1, 2, 3, 4, 5. Run 3. 1, 2, 3. Now that point right there is 3, 3. If we put 3 in for the x and 3 in for the y and we did the math, it should come out to be 6 because we could check it that way. Rise 5, 1, 2, 3, 4, 5, run 3. And I'm going to actually go down 5, 1, 2, 3, 4, 5, and over 3. And that should be on the same line. And that helps me be consistent with my drawing of the line. Put arrows on the ends because it goes on forever. And there we go. There it is. Fantastic. So I alluded to something just a minute ago that will help us graph lines in a different way.